Welcome to the lecture of production of automotive components. So in the last lecture we discussed about material selection and manufacturing methods. In this lecture we'll be talking about the engine block. How is the engine block manufactured, which is basically by casting, and we'll be talking about the two types, which is conventional pattern and expendable pattern casting. So first, talking about the engine block. You know that engine block is the major component in an engine which gives the space for fixing up the cylinder head, valves, and where the piston is being connecting rod, so that serves as a base component, and that is manufactured by using casting. Casting is one of the oldest processes, and you know that in casting molten metal is poured into a mold cavity, and when this molten metal solidifies, it takes the shape of the cavity, and finally you get the product, which is basically in the shape of the cavity. So that is what is casting. So if you see this process, there can be two different ways of doing it. That is by using a conventional pattern, and second is by using expendable pattern. So conventional pattern is nothing but a permanent mold pattern, but expendable, as the name suggests, expendable is nothing but anything that can be easily destroyed after its use. So here in this we'll be using this pattern for the casting purpose, after which it will be destroyed. So we'll see how that happens. Below you can see the picture of an engine block with 3 cylinders. So talking about the first type, which is a conventional or permanent mold. So in this, the mold is basically made up of metals which can maintain the strength even at high temperatures, because when you pour the molten metal, it is of a high temperature, so the mold cavity has to withstand this temperature, and these are permanent, which means they can be used again and again, and it is usually designed so that the casting can be easily removed, and then this mold can be used for the next casting. And metal molds are mostly used because they are better conductors than the expendable molds, and in case of metal molds, solidifying also takes place at a very higher rate of cooling, and this will affect the components' mechanical properties. So in detail, it's the microstructure or the grain size within the casting. So if it's very small, the casting would be very strong. So that is about the conventional mold, where the mold is permanent and it can be used repeatedly. Below you can see the figure in which the cavity is shown, into which the molten metal is poured. As you can see over here, this is a conventional mold where the pattern is permanent and it can be reused again and again. So once it solidifies, you remove the force, and then this component can be taken outside. So that is how engine block is manufactured using the conventional mold process. The next comes the expendable molds. So if you see expendable molds, as I already told, it is a material which will be destroyed at the end of its use. So molds are usually made up of sand, plaster ceramics, or all these materials which are binded together, and a sand mold typically consists of 90% sand, 7% clay, and 3% water. And all these materials should be capable of withstanding high temperatures, and they are known as refractories. And once the casting is solidified, what happens is the mold is broken up completely. So this is what is expendable. That mold is broken up and it is being destroyed. So that is why the name expendable. And in some cases the pattern is itself expendable. So in terms of sand and shell casting, the mold is expendable, but the pattern can be reused for several molds, and those processes are known as expendable mold permanent pattern casting process. So pattern is nothing but the component which basically has the shape It's basically a replica or a prototype of the casting component which you need. That you call it as pattern. So surrounding the pattern, what you have is nothing but the mold. If it can be destroyed, it is expendable mold. And one example for expendable mold, expendable pattern process is investment casting. So in this, the mold will also be destroyed once the casting is done, and also the pattern will also be destroyed. So here you can see the pattern making process, which is nothing but the casting process of an engine block. So you can see that the pattern is made up of an expendable material, which is nothing but lost foam, which we'll be discussing in the next slide. So expendable pattern is the pattern which itself will be destroyed when the metal is poured into it. So that is why it is known as evaporative pattern. So you keep a replica of the casting product which you desire, which is nothing but the pattern, and that pattern will evaporate, and this casting is known as also evaporative casting or lost foam process. So what we use is nothing but polystyrene pattern, and that will basically evaporate when it comes in contact with the molten metal that is poured into the cavity for the casting process. So this polystyrene comes in the form of beads, and when they are preheated, they will expand, become like a vapor, and then take the whole shape of the die cavity. And then after the die is cooled, the polystyrene pattern can be removed, and then it is placed in a flask which is covered by fine sand, and this sand will make up the whole casting base. So when this sand is compacted properly, so the polystyrene pattern is completely covered with the sand. So as you remember, in case of sand casting, you keep a pattern and then you have to pour sand into that, and then you just make sure that the sand is compacted. So similarly, that pattern is made up of polystyrene here. And when you pour the molten metal, what happens is this polystyrene pattern will evaporate, and then the whole cavity will be formed, which will be filled by the molten metal, and this molten metal cools faster if it were poured directly into an empty cavity. So in the conventional methods where you have an empty cavity, if you pour it, it will take a longer time for it to cool, but if you pour it in this lost foam process, then the cooling process is faster. So in this slide, you will be having a video which will be about the engine block casting process, what we discussed in the last slide. Just click on the black box which you can see, and then you will have a video that is following, which talks about the lost foam process of engine block casting.
The innovative metal casting process of the future is here today. Lost foam casting has been slow to develop, but is finally a technical and commercial success. The name lost foam refers to the process of creating a foam model of the casting and then replacing the foam with molten metal. The process begins with polymer beads, which must be expanded to a controlled low density for molding. The beads as purchased have a cellular structure and contain a gas or blowing agent, usually pentane. In a pre-expander, steam is used to heat the beads, softening the polymer and expanding the gas. Control of density and bead distribution is critical in this operation. After pre-expansion, the beads must be stored for stabilization before use in molding. A distribution system delivers beads from storage to the molding machines. Tooling mounted in a molding machine provides a cavity in the shape of the casting or a portion of the casting. The preheated cavity is completely filled with beads through fill guns. Steam is again used for heat and now enters the cavity through vents and further heats the tool from the back side. This causes the beads to expand into the voids and to fuse together. The fused foam and the tool are cooled by water and vacuum to allow the foam to be removed from the tool. Tooling is typically machined polished aluminum, producing very precise dimensions, and an unusual but smooth surface finish with precise detail. The tooling is exposed to only non-abrasive beads and steam temperatures, and usually maintains surface finish and original dimensional accuracy throughout an extremely long life. Foams are normally aged, usually in a controlled warm air oven, to stabilize the dimensions. Foams can be molded in one piece, sometimes using movable pulls. Multiple pieces can be glued together to form extremely complex parts with internal passages and detail sometimes not feasible in other processes. Gluing is normally done with special hot melt glue, printed on the parting line between foam slices. Excellent dimensional tolerances, appearance and casting quality can be achieved when flat glue lines are properly designed and when tooling and equipment have proper precision and control. Foam replicas are then assembled with a gating system to form a cluster of parts to be produced in one flask. This can be done manually or by machine. Foams or clusters are then dipped in a water-based refractory coating which covers all surfaces of the foam, including internal passages. The coating will now have an internal surface equal to the outside surface of the foam. The wet, coated foam cluster is then placed in a drying oven to remove the water. Ideal process control and throughput are achieved with dehumidification and internal humidity control. The coated dried cluster is placed in a special steel flask, either manually or automatically. Dry sand with no additives is then rained around the cluster and vibration is applied to the flask. Inside, the vibration of the flask causes a layer of sand near the surface to fluidize. In this layer, the sand flows around and into the inside passages of the foam. The sand level rises as additional sand is rained in. Below the fluidized layer, the weight of sand above, together with vibration, causes the sand grains to move closer together, compacting them. The vibration and the flowability of dry sand causes densities of the compacted sand around the coated foam to be 10 to 15% higher than in other sand processes. Proper control of vibration and sand fill can ensure low foam distortion and full rigid backing of the coating. Some systems use synthetic mullite in place of sand to further improve cycle times and dimensional tolerances. After fill and compaction, molten metal is poured into the cluster. As the liquid metal moves inside the coating, the heat energy causes the foam to liquefy, evaporate, and break down chemically. The temperature of the metal poured and the foam characteristics will determine how much liquid, vapor, and gas will be formed. Special coatings have now been developed for various types of castings, which have capillary action to absorb liquids, as well as permeability to allow passage of vapors and gases. Because there is nothing in the sand to burn out, creating collapse or mold wall movement, dimensions are very accurate. After the poured cluster is allowed to solidify, the flask can be simply tipped over and the unbonded sand flows out. No additional violent shakeout or core removal are necessary. Because the foam pattern is left in the mold, no parting line is needed. This allows orientation of the casting to be more flexible and permits clustering, which produces more parts in a given mold area. More parts per mold means higher production at slower mold per hour rates. The dry, unbonded sand is easily recycled with minimum energy consumption. The mass of foam is low compared to the binders burned out in other sand processes, reducing emissions. This makes lost foam an energy and environmentally friendly process. Because there are no cores, core defects and fins are eliminated.